Hello and welcome to my physics lab, Lab 1, constant velocity. So today we're going to be talking about constant velocity, and the goals of this experiment are to observe the motion of an object at a constant velocity. This object being a charging block, which I have in my room. We will expect the motion to change at a constant rate and for the velocity not to change at all because there are no obvious forces acting on it. I'm not pushing it, nothing is pulling it, nothing like that. Some things that we need to assume are that there are negligible friction and air resistance, and that the object does not move in the y or z axis, which I really hope is not moving in the z axis. Um, as far as key concepts that you need to understand for this lab, you need to understand Newton's first law: an object in motion remains in motion at a constant speed unless acted upon by another force. As the normal force of the floor and gravity are essentially equaling each other out, there is no unbalanced force here, so it does continue in that straight line. The net force in that case would be zero, and the change in position constant. So we can use the velocity update formula here. The final velocity equals initial plus the net force divided by the mass of the object times the change in time. As the net force is zero, you can essentially eliminate this from the equation. And then this is used for our position update formula, which is what we will be observing in the graph. So to understand this problem, again, we have the normal force of the floor, the force of gravity pulling it down, and as a result, there is a net force of zero on the object. So it is allowed to continue at whatever velocity it starts with. So as far as the tracker analysis, which I will go to now, you can see here that the object continues at a pretty consistent rate and up until pretty much the very end of this video. And as a result, it has a very linear progression in the x-axis. And what is that basically is indicating is that the velocity is constant, and which again makes sense according to our theory. Um, that basically there is no force, so there shouldn't really be a change in the velocity. So going forward, we can now compare this to the computational model, which I have here. This computational model is defined by the mass of the ball, which doesn't really matter in this case for the simulation, but would just be the mass of the object that I have. And then we have the initial position, which is measured in the program, as well as its initial velocity here. And I can essentially find this initial velocity by taking the first two positions and taking their difference and then dividing it by the change in time, and that gets that instantaneous velocity. And because the velocity is not changing, there's no additional force. This will be consistent throughout the experiment, and this is representative of the code. I upped the time in order to get a more accurate representation here, and I also defined the velocity of the ball according to and the position according to the formulas that we went over earlier. So going forward, here are essentially the results of the computational model, which actually, let me show you how it functions. You can see it's going in a straight line, which is pretty much what we observed in reality, and we have this very linear slope here. Again, here is a handful of the data, and it projected on a graph here. You can see this constant velocity. Here it is again compared to the actual reality, which does dip a little bit at the end. And you can compare it here. There's a slight difference. This is pretty much zero. Then there's a difference of about a centimeter, I think, or maybe a millimeter. And that's pretty consistent until the very end where friction becomes actually important. So in the beginning of the experiment, the initial velocity, reality, and computational model were very consistent. They were the same as each other. But as it began to go on, the speed began to diverge, and this is due to friction. And some errors in this were that the tracker is not really perfect, that the object may have gone into the y-axis, maybe even a little bit in the z-axis. But most importantly, that friction cannot be negligent in most circumstances in the real world. If the axes were flipped, this would be going in the opposite direction. And that's basically just because pushing it the other way would just make it go the other way. It's as simple as that. And what does this mean? Can you accurately describe all the net forces? Well, you can try. A perfectly accurate model is not super possible because of the sheer quantity of objects in the universe which are all affecting each other. But when you approximate these values and get a net force, these usually cancel out because the gravitational force and the normal force um, essentially prevent the ball from flying into the air, which we do not observe in reality, or destroying my floor, which thankfully we don't observe. friction and air resistance are also something that would improve the experiment's accuracy, and they would be in the negative direction. So they would be a force that we would have to calculate in a follow-up experiment. Thank you so much for watching my video. I hope it was informative.